Welcome to 47th lecture. We have been discussing in general, actually it should come under that topic, phase conversion, and we have studied 3 phase to 2 phase, and we have completed this, and this is called Scott connection. Got the point. Similarly, these connections, another connection is that 3 phase to say 6 phase conversion. 3 phase supply is there, you require a 6 phase supply. Anyway, there are as such motors which are 6 phases, 6 phase balanced, 3 phase balanced to 6 phase balanced system. 6 phase balanced system will be what? There will be 6 voltage phasors which will be 60 degree apart. 3 phase system, 3 voltage phasors of equal magnitude 120 degree apart. Now, 3 phase to 6 phase conversion were used very much at a certain point of time. For example, we have a 3 phase to DC conversion by using a diode bridge. 3 phase supply you give, you will get a DC supply. But if you increase the number of phases of that AC to DC conversion using diodes, 6 phase will be always better. You will get better DC there, is not? The ripples available is not 120 degree apart, every 60 degree something you will get. Anyway, I will just tell you how to suppose 3 phase to 6 phase I want to do. What I will do? I will take 2 3 phase transformer, not 2 3 phase transformer, one 3 phase transformer with 2 secondary coils, okay? Identical secondary coils. For example, these are the primaries we now know. So, I will draw. This is quite simple, I mean to understand. This is suppose dot, dot, etcetera. So, every time I am drawing dot, so that you also see its importance, it is necessary to put the dots A 1, A 2, and then this is A 1, A 2, A 3, A 4. But and these 2 coils are identical. Okay. These are all N 1 turns, these are N 2 N 2 turns, B 1, B 2, C 1, C 2, then this is B 1, B 2, C 1, C 2, and no B 3, B 4, and this is C 1, C 2, C 3, C 4, clear. And what you do is this, you connect this in star. So, I know the phasor diagram. So, phasor diagram will be primary side, it will be supply is AS, BS, CS. So, AS here supply, BS, CS, and AS is nothing but A 1, B 1, C 1, and this is A 2, B 2, C 2. Now, what you do is this, you connect the secondaries, these 2 groups in stars, but one connection you make y by 0 and the other as y by 6, and you are done. Why? Because if you join these 3, then you get y by 0, is not, and your this voltage will be this, say A 1, B 1, and C 1, and the other group what you do, that also you connect in star, but this time join these dot terminals A 3, B 3, C 3, then its phasor diagram will come out to be this one, y y 6. So, this is primary was y, y y 6, this primary is y blue, I will write. This is y y 0. Then what? The naming of these terminals will be, this is A 2, is not? This is B 2, oh not A 2, A 4, B 4, C 4, and then you join these two neutrals, these two you short. Then this point becomes a global neutral on the secondary side, where A 3, B 3, C 3 and A 2, B 2, C 2 are shorted. So, if you see this voltage waveform of this terminal, they will be 60 degree apart of same magnitude. So, you have been able to generate 6 voltages on the secondary side, which are of equal magnitude and 60 degree phase difference. So, balanced 6 phase voltage, 6 phase voltage. We will not discuss much more, but what I am telling is what happens is this, in the see diode bridge, and this maybe the names of this may be changed a bit. So, that what I will tell, what I am telling is, you name this output terminals A 1 to be A, suppose. Okay. This C 4 you say B phase of the secondary side, this is C phase, this is D phase, this is A B C D E, and this is F phase. I could rename them. Then I have got these 6 voltages A B C D E F, whose magnitudes are same and so on. So, what I will do is this, I will connect it, and it has also got a neutral. So, I have a supply system now, whose terminals are A, B, C, D, E, F, and also neutral. Got the point? What you do now? You connect diodes. One of the applications I am telling, you connect diodes. And then connect the resistance load, where you want to get DC, and this point connect it to neutral. Things will work. Okay. So, anyway, so phase conversion 3 phase to 6 phase can be done this way. Another way you can do, I hope you have now got the idea. Can I do it by using some delta connection? Yes, connect one group as D D 0, another as D D 6. I will not do that, but I will tell you the end results. One group, this you connect in delta D D 0 and D D 6, this group. So, the output phasors will be like this then. Suppose this is D D 6, you work out that on your own, and this is black. This black one is D D 0, Then also these terminals, of course, there is no scope for connecting neutral now. This is delta, this is delta. Where is its neutral? Nothing to be joined here, as I have joined here. So, if you connect a voltmeter, for example, here, even when no load is connected, voltmeter will read this much. This voltmeter will read, but here if you connect the voltmeter here, circuit is not completed, because two apparently other thing. So, what is to be done? You will get balanced voltages here provided load is connected. So, connect a balanced 6 phase load, clear. So, return path will be obtained, 6 rheostat, you can show it in I should not call it delta, like a polygon, it will look like 1, 2, I mean equivalent resistance 3, 4, 5, 6. Suppose this is my impedance, load impedance, these 6 terminals you join there, then the circuit will be complete at balanced 6 phase voltage you have been able to apply it. Anyway, see this 3 phase transformer connection is a very nice subject, and lot of further more connections are there, using many small windings, doing this, adding that phasors. For example, one of such examples were traditional zigzag connection, as I told you. But it is in nutshell, whatever knowledge you have acquired, I hope you, if you read those things, some advanced topics on transformer winding connections, incorporating more coils into it, you can do several other things, that is there, but these are the main things, okay? And you will be able to, I think, solve simple numerical problems on this. So, this is the phase conversion thing, 3 phase to 2 phase, then 3 phase to 6 phase, and so on. One can go on doing like this. Now, our next topic will be the parallel operation of transformers. Okay. That is another important topic. Okay. Our next new topics is parallel operation. Of transformer. Achha, before I do the parallel operation of transformer, I am sorry, let me tell you one thing. What is that thing? That is, look here, if it is a single phase transformer, I must know the equivalent circuit parameters, and this can be measured by doing some simple experiments like open circuit and short circuit test. Now, what do I do for a 3 phase transformer, and how to find out the equivalent circuit parameters of a 3 phase transformers? Suppose I say the transformer rating is known, let me write some rating, suppose say 30 kVA, 30 kVA, just writing some numbers, say 400 volt stroke 200 volt, 3 phase, 50 hertz, calculator ache, 50 hertz transformer. Anyway, calculator is not needed. Okay. Now, and I say that the transformer is star connected, it is given star connected, and it is a 3 phase transformer, not a bank of 3 single phase transformers put together. So, what do I know about these things? about these things I know that this is the total KVA, this is line to line voltage mind you of the HV side, this is line to line voltage. So, in the same way you carried out the open circuit and short circuit test, here also you should do the same thing. So, what do you do? The transformer you connect generally as I told you from the LV side you carry out the no load test. So, suppose this side is LV, this side is HV. Therefore, to carry out the no load test, what I will be doing is this I will apply rated voltage, What is the rated voltage? 100 volt. Where it should be applied? Between line to lines. See, that is what I am telling, this is line to line voltage. So, it does not tell you the 200 volt, you apply rated voltage and 200 volt is the line to line voltage. This 200 volt never tells you that this LV side voltage rating is 200 volt, 200 by root 3 is the rated voltage of the LV side, but anyway 200 volt you apply. You connect 3 phase 200 volt and you connect ammeter and also wattmeter, and better connect 2 wattmeters because it is a 3 phase system. So, note down I naught and W naught wattmeter reading and this one. Secondary side open circuit and applied voltage of course must be rate. So, you have a voltmeter as well connected here. So, you know applied voltage. Now, then what you do, you calculate the parameters in this way on the per phase basis. How it is calculated? First thing is root 3 VLL, this ammeter rating I naught, no load current it will draw into cosine theta naught, and during open circuit test it is only core loss matters, is not. Copper loss we neglect because no load current is very small, maybe 2 to 5% the rated current. How much is the rated current? As I told you, always do this HV. So, rated current of HV side this I will come. So, no load current will be small and you calculate this, and this must be W naught, and from this you will be able to calculate cosine theta naught, from that you will be able to calculate sin theta naught, then you will be able to. So, per phase voltage if you have applied per phase equivalent circuit. So, V phase and this will be your no load current, then this is theta naught, just like single phase. Then break it up into 2 component, that is magnetizing and ICL, and then calculate ICL. This is theta naught, this is theta naught, ICL is equal to I naught cosine theta naught, is not, I naught cosine theta naught, and I m is I naught sin theta naught. And once you do that, you will be able to calculate RCL 1. Suppose you say LV side is 1. So, RCL 1 will be the applied voltage V divided by ICL, and XM 1 will be equal to V by IM. That is all. Similarly, while doing short circuit test, what should I do? Generally, from the HV side, the short circuit test is done, HV side, and LV side is kept shorted. Of course, for this rating it does not really matter from, because it is only 200 volt, 400 volt. In the laboratory all the voltages are available, and hopefully the meters required will be also available there. So there what you do, this LV side you can short them. The moment you short the LV side, can I apply rated voltage 400 volt here? Never, because it will then draw very large current. Current will be only limited by its leakage impedance. So, here you must have a 3-phase auto transformer to apply rather small voltage. Oh, sorry. And auto transformer. It is not auto transformer, I should call it variac, 3-phase variac, because you must be knowing the difference between a variac and an auto transformer. Auto transformer means this winding, you are using different section of wires, you get advantage. Anyway, so you measure the voltmeter reading here VSC, you record the current, you connect 2 wattmeters. See, this W naught is equal to W 1 plus W 2, algebraic sum. So, this is W 1 plus W 2, and while using the wattmeters it is better, because during open circuit test power factor is rather small, use a low power factor wattmeter. Anyway, those are details of the experiment, but you somehow note down this total reading W naught. Here also connect better 3-phase transformer, 2 wattmeters, current coil and pressure coil. Note down ammeter reading and call this current ISC. How much voltage should I apply so that rated current flows? What is the rated current on the HV side? IHV rated. It will be how much? 30, 1, 2, 3, 30,000 kVA by root 3 into 400, is not approximately how much it will come? 43 ampere, say 43 ampere. So, you have to choose an ammeter which can read 50 ampere, say, and similarly wattmeter, current coil, but line to line voltage, voltmeter rating should be very small, maybe 5-10% of 400 volt. 5% of 400 volt is only 20 volt. Voltage required will be pretty small. So, that current, rated current will be circulated. Secondary will also carry rated current primary. So, that copper loss will be there. So, wattmeter once again will read this W 1, W 2, sum of these two, W 1 plus W 2 will give you the copper loss at rated current. We neglect the core loss. Why? Because rated voltage applied is very small. Flux is only a few percentage of the rated flux, when you apply rated voltage, rated frequency. Therefore, copper loss we assume this, and then this ISC square into R, this side I have called 1, this side is 2. So, ISC square R E 2 will be this, from which R E 2 is known, R E 2 is known. Into 3, okay, total copper loss. Similarly, once you get RE 2, you have to calculate JD 2. JD 2 will be this impedance. So, what is the impedance per phase? It will be applied voltage VSC line to line you have measured by root 3 divided by ISC. And once you get, so from this RE2 is known, from this WSC. So, RE2 known, then XE2 can be separated, which is equal to root over Z is 2 square minus RE2 square. But only thing you should be careful that per phase equivalent circuit, the moment you carry out test, one test from LV side, another test from HV side, and it is your duty now to choose from which side you will draw the equivalent circuit. This I told you in this earlier class. Therefore, if I want to draw the equivalent circuit referred to the LV side, then you have to transform these parameters in that sense. What is the turns ratio here? Turns ratio of the winding, if the connections are same, star to star or delta to delta, then the turns ratio will be the line to line voltage ratios, is not. So, that is the thing. Now, the question is what happens? So, per phase equivalent circuit, you have to draw per phase. See, worked out problems from books as well as in my notes I have included some problems, you go through that. Per phase equivalent circuit we refer to. Now, suppose I say that the transformer is star delta, okay. Same rating, what I told 30 kVA. Suppose I say that 30 kVA, 400 volt, 200 volt, and the connection is star delta. Then what do I do? How to draw the equivalent circuit like that? Okay, you have to carry out the open circuit and short circuit test, because the readings we are taking are only the line readings, is not. We are, while carrying out the test, I am measuring the line quantities. In fact, you do not need that information whether inside this is star or delta connected, is not. We have connected everything in line, ammeter, line to line voltage I measured. I never asked where the neutral is, I will measure this phase voltage. Got the point. So, one way of looking at the thing is carry out the test in the same way as you have done and imagine as if it is star connected and tell that per phase equivalent circuit. Listen to me carefully what I am telling. Is not, see, the transformer is now star and this side is delta. I can always imagine that no, it is so far as measurement is concerned, it does not matter. Oh, you can equivalent to this side, you can consider it to be some equivalent star. And then calculate the parameters in the same way, because what you are doing, you are measuring total power drawn by that 3-phase connection, which is star shown here during the no load test. Suppose I carry out the no load test, what do I do? This is your actual transformer, I will connect 2 wattmeters here. Let me slightly clean this thing. Try to get the idea, I will not tell, it is in fact not needed so much pointing out, but it should be understood what we are doing. Ammeter you connect, rated voltage you apply 200 volt while doing open circuit test. this side is open, who bothers? That is fine. But what I am telling, you can always imagine this to be star connected while calculating the parameters and live with them. Another way of doing it that is looks like more appropriate, it is like this, that is, I will carry out the test, no doubt. I will say that look, this is the no load current you are carrying. I will start calculating per phase. What I will do? Per phase voltage applied to this winding is how much? 200 volt. I will say this is I naught by root 3. If it is delta connection, I know that. So, through the winding I naught by 3 root 3 is going. Okay. This total wattmeter reading during open circuit test will be the sum of the core losses of all the 3 phases, is not. Therefore, this voltage and this W 1 plus W 2 by 3 I will do and leave here. Okay, it is a single phase transformer, this is its primary, this one is secondary, whatever it is, one of the coils, and power absorbed by this is this one, and whatever is the power factor angle I will calculate. So, in that case I will do it like this, that is this by 3, I will say 3, not 3, V naught into I naught by root 3, this is this current, I naught by root 3 I will take, whatever it is that number, I mean I should not translate it to I naught, V I naught and cosine theta naught, and calculate cosine theta naught, and then I will calculate I naught by root 3 sin theta naught to get magnetizing current and this one, and I will, while drawing the equivalent circuit, refer to this side 200 volt. Only thing is, in that case turns ratio will be 200 by 100 by root 3, that you must understand. Anyway, solve some problems on open circuit short circuit test, because it is per phase basis the analysis is done. Regulation problem, this that will be all similar, because single phase transformer, it can be considered to be a single phase transformer, 3 such units. Okay, think about it, and we will continue in my next lecture the parallel operation as I told you. Thank you.